3 tajuk yang saya belum cover, 4. Tapi sebab ada pilihan. Satu ialah Higgs boson punya symmetry breaking mechanism. Sebetulnya tajuk ni agak susah, tapi sebab saya dah boring dah, saya tak tahu soalan yang lebih kurang sama. Yang ni adalah yang baru dan disebabkan ada penemuan Higgs boson. Okay. So saya nak masukkan. So kalau saya tak sempat cover hari ni, sila baca dalam Wikipedia. Itu yang mudah. Yang kalau selain daripada Wikipedia memang tak nak baca. Wikipedia ni macam mana pun dia akan mudahkan tajuk-tajuk ni. Yang kedua yang saya akan cover hari ini ialah Grand Unified Theory, Grand Unification. Ini pun definitely akan keluar. Dan satu lagi ialah bahagian kecil saja tapi penting juga sebab akan keluar, iaitu supersymmetry. Ini semua ni saya belum cover. Jadi kalau saya tak boleh hari ini, saya minta maaf. Glashawan bersalah. Okay. Yang ni akan keluar. CP violation yang saya cover minggu lepas. And then of course quantum chromodynamic. Dan ini termasuk hal-hal seperti CKM matrix lah dan sebagainya, asymptotic freedom dan sebagainya. Dan some example of quark line diagram lah, macam flavor changing dan sebagainya melalui W dan sebagainya. Itu banyaklah yang dikaitkan dengan ni. Sorry, yang flavor changing ni elektroweak. Dan of course CP violation satu hal, tapi parity violation ada yang Madam punya eksperimen. Yang ini termasuk octet, nonet semua tu lah yang ni struktur tu. And then of course yang paling biasa yang satu lagi adalah standard model punya group structure. Strong weak EM. Sebetulnya that is the first part of the grand unification. It is, let me just put point 1. It is unification of the theories of fundamental forces namely EM, weak and strong interaction. And this has been achieved via the so-called so far, number one, why gravity has not been included? Because of course the goal of grand unification is actually to include also gravity. But nobody really these days understand quantization of gravity. So let me just check you out that EM plus weak interaction has been achieved by the GWS theory. So this is the first unification. Now, GWS plus QCD not achieved yet. And then, but the platform already there. That is the standard model. So the standard model is the platform for unification, but still not there. And then gravity. So GWS plus QCD plus gravity. This is the final theory. Final theory of unification. This one, you don't go directly like this. Yeah, you go this one. People say we are string theory. You cannot go just this way. That's a dream. So basically, the idea is this grand unified group. Yeah, it is. So you have a grand unified group in higher dimension. In high dimension, and then it break up into the one that you have. This is a kind of broken symmetry. The one that you have in the standard model, SU3 times SU2 times U1. So that is. So this is a dream to find that grand unified group. What is clear is that superstring has a group of E8 cross E8. The exceptional group E8 E8. Let denote the gauge coupling by G1, G2, G3. Or is the other way around? G1, no, G3, G2, G1. SU3, SU2, U1. The one which is the standard model. This is the standard model. Coupling, okay, can be what you call it, reformulated or stated in terms of what you call gauge running of the gauge coupling. So this running of the gauge coupling is written in terms of what you call a renormalization group equation. I will tell you what all that means. The reason being, all this coupling is given or depend on the energy. You all know that the energy to probe electromagnetism very low. You don't need to do a high energy collision to see the effect of a photon, because basically when we study the coupling, we are looking at the behavior of the gauge boson. Okay. For the weak interaction, even though you call it is weak, but to see the gauge boson, you need to do high energy experiment so that the W and the Z will appear. Okay. And same the QCD, you need to do a very high energy collision to really see the effect of the gluon. Okay. So those require high energy. So different energies are required to see the effect of the boson of each of these forces. So that is why renormalization group is important to be used to see the effect of this, or to understand the effect of this change in coupling due to change in energy. Renormalization. Renormalization means that at different energy and at different scale length, you have different effect, different coupling. Okay, but the equation is the same. So the renormalization group equation is a kind of master equation. Okay, a kind of master equation that is true for all these forces. But you need to consider only for the different energy or different forces. You need to look at the different energy. So this alpha I here is actually the Gi. Yeah? Whether so I is 1, 2, 3. Okay. Z boson. Mass of the Z boson. So the Z boson. You know, the electroweak theory or the GWS theory is the first to combine EM and weak. So these people, Glashow and Salam, are the first people to realize this so-called renormalization behavior. So this is, I put here, standard model, SM. Then the value of the BI in the standard model, derived by these three people. But you know, there is a possible correction. And this is when we consider the idea of supersymmetry. So itu satu hal. Whether I can talk about supersymmetry today, I'm not sure. But it's not that important. But this one can be written as 1/16 pi square with some correction. 33/5 1 minus 3 in the minimal supersymmetric model, MSSM, suka Malaysia. It is a minimal supersymmetric model. Okay. Yang ini standard model. Okay. And this difference is due to what you call a super partner in MSSM. Why super partner? Dalam supersymmetry ini, where using this idea of supersymmetry, the fermion and boson, they are on the same level. Okay? And because of this, neutrino dan sebagainya ada. All the, what you call it, all the gauge boson will have a super partner. Contohnya graviton. Kalau betul lah wujud graviton atau gravity wave itu, maka super partner dia adalah gravitino. Begitu. Begitu juga dengan semua ada partner. Neutrino ada neutralino kawan dia. Jadi sekarang ni sebab tak ada orang yang jumpa. So, in many of the grand unification theories, ya, bukan ada satu dua, mungkin ada beberapa that try to arrive at this the coupling is, I think, almost confirmed, but how do you approach or understand the way it is unified? Yeah? They are, so in many grand unified theory, the three gauge coupling are predicted to meet at some high energy unification scale, above which the three interactions are unified, and grand unified symmetry breaking can be ignored. So you can say that currently, kalau kita, so let's, in the standard model, if we plot the alpha I, and the alpha I is effectively the GI. Okay, it's just the way we plot it, and in fact it is the inverse, because it is 1 over and 1 over. Oh, the Q actually is the energy. Q is, I forgot to write here, is the energy scale. As I said, if you go to higher energy, then it will be different. Now, and then we plot against the Q, the energy, in log, say log 10 of Q. And this Q is in GeV, Geiger electron volt. You will see that using this in the standard model, this dimensionless, actually, this 1 over alpha I 0, 20, 40, 60, 80, 40, 60, 80. And this 0, 5, 10, 15, 20. The log quite big. So you will see that see, this is the line of the alpha 3 minus 1. Alpha 2. This is alpha 2 minus 1. This is alpha 3 minus 1. And then alpha 1 minus 1. So it seems that whereas alpha 2 and alpha 3 meet somewhere at this scale, alpha 1 is out. Alpha 1 is actually EM. Alpha 2 is electromagnetism. Sorry, alpha 2 is weak and alpha 3 is strong. So in the standard model, this is one reason why the standard model is not believed to be the final. There is apa yang people say beyond the standard model. I mean, there are more than 10 reasons why standard model is not There are 10 reasons why the standard model is not satisfactory. More than 10 reasons. Okay. One reason is this. Using a standard model, you will see that the so-called running coupling constant, as a function of energy Q, they don't meet. So, hancur harapan grand unification. The so-called the supersymmetric standard model. Okay. Where in this model, the gauge supersymmetry, SUSY, the Z menjadi satu, Z particle dijadikan sebagai ikon dia, jadi benchmark dia untuk dikatakan, katakan Z particle ni adalah gauge boson untuk supersymmetric, katakan. So dia pegang kat situ. So you will see that if you do that adjustment, so this is called the supersymmetric standard model. The standard model with some idea of supersymmetry. They will meet somewhere here at the 10 to the 19. Itu yang cantik. Grand unification. Okay. Berlaku di titik itu. Tapi setakat ni kita belum sampai dalam Large Hadron Collider. Dalam Large Hadron Collider kita belum sampai 10 to the 19 GeV. Terlalu besar nak sampai. So let me just talk some of the attempt at this. So this some grand unified theories. So ini percubaan ini. So I will just list down. So A here, patutnya ada B. Some grand unified theories. Ini adalah SU4 C ini chiral. Susah nak cerita saya. And then chiral satu hal. Satu lagi SU2 tapi left. And then SU2 right. Okay. So this one was the so-called Pati and Salam model, 1974. Pati and Salam ni, Abdul Salam cuba unify quark and lepton. The SU4C group extend the QCD to include a fourth color associated with the lepton. So that, for example, the three color of U quark could be related to the neutrino by the symmetry of the new interaction. So this is just an attempt, yeah, without supersymmetry. So this one. So three color for quark plus one color for lepton. So ada satu color pula extra untuk lepton. The other one is the SU5 model of Georgi and Glasgow. SU5 model by Georgi and Glasgow. Ini pun 1974 juga ni, masing-masing berlawan-lawan ni. So yang ni, this SU5 is broken into SU3 cross SU2 cross U1. Actually, SU5 theory of Georgi and Glasgow ni adalah satu macam model yang pertama yang dapat menggabungkan strong, weak and electromagnetic gauge coupling. Unfortunately, they did not predict the W and the Z, and the unification scale is mx at 10 to the 14 to 15 GeV. Quark, lepton and their antiparticle are combined in the same SU5 multiplet, leading to charge quantization. There are also new interaction mediated by this X particle, and then there also ada satu yang dipanggil Y boson. So there is another one, kawan dia, Y boson of the same. So because nothing can be seen at this scale, so this theory is wrong. And then this model also predict proton decay. But with a very long lifetime, tau p of the order of mx to the power of 4 divided by alpha square and p to the power of 5, and that's roughly about 10 to the 29 years. In real experiment, the super Kamiokande, so number one, mx, x particle, y particle is not seen. The other thing is that super Kamiokande experiment put the decay of proton to be the tau p, the lifetime, to be greater than 1.3 times 10 to the 34 years. So this prediction is way out. So I don't want to go into the detail of the SU5 model, but there are such model. And then of course all these model has their definite Lagrangian density, which you can employ symmetry breaking and whatever to see the match of the gauge boson, or to estimate that. So basically SU5 is the first sort of successful, almost, I would say almost there. Almost there. But still it's wrong. They did not predict the Higgs boson, for example. Nor do they manage to see the W and the Z. Neither do they predict the W and the Z. So the detail of this theory is somehow wrong. Okay? Whereas the GWS, even though they have this structure, they get the right figure, the right prediction for WZ and also all the other detail particle. Of course, another, so basically better put this is the first attempt, some attempt. Of course, there is another way for you to do grand unification. One is to, in fact, when Georgi and Glasgow managed to show that it has this structure and, you know, almost there, I would say, yeah, people will try to copy this. So they say, well, you know, SU5 might not be so correct because the group is not large enough. So there are people who say that so some people will use a group of SO10, or this is the first time that they use an exceptional group of 6 members which embed SU5. The special unity group with 5 members are embedded inside these 2 groups. So people say, oh, because this one is not predictive enough, we say maybe it is embedded in a larger group, and let's work on this larger group and see what we get out of this. So, for example, the symmetry breaking of SO10 to SU5 cross U1 X 1X, because they predict that due to this symmetry breaking there is a neutral gauge boson. Called ZX.